In addition to performing hypothesis tests on the mean, we can also perform hypothesis tests on the variance and other statistics. So I'm going to talk about how we can do this in this screencast. I've got an example here to start us off. The most common thickness of plastic sheeting is 6 mil, which means that the thickness is actually 0.006 inches. It's very important that the variability of the sheeting be within a certain amount, 0.25 square mils. You suspect that the variance is significantly greater than 0.25 square mils, so you take a random sample of 10 pieces of plastic sheeting and you obtain the following measurements. What we're trying to do is to determine if there's evidence to support that the variance is greater than 0.25 square mils. In order to perform this test, we're going to base this on the chi-squared distribution. Remember, if we took a population and we took samples from that population, and if we did this repeated times, here we have a sample of size 10, and if we standardized our sample variance to compute this chi-squared statistic, and if we did this many, many times, sample size equals 10, we would get a distribution of this standardized sample variance, which is known as chi-squared. And that's if the true population variance is what we propose. Now, if the true population variance is significantly larger than what we propose in the denominator here, then our sample statistics, our chi-squared values, are going to tend to be in the upper part of this tail. They're going to be higher than what we would expect based upon that population variance, that hypothesized population variance. If the true population variance is less than what we propose or we believe it is, then when we compute these chi-squared statistics, our chi-squared values are going to consistently be lower down in this tail. And so this kind of forms the foundation for hypothesis testing on the variance. To perform these tests on the variance, there are three forms. There's a two-tailed test, where the alternate hypothesis is that the variance is not equal to what we propose. Sigma naught squared is just our proposed or our assumed population variance. We have a upper-tailed test where we propose that the variance is greater than the null population variance. And then we have a lower-tailed test. In all of these cases, we calculate a test statistic, so we convert our sample variance to a chi-squared variable. This is essentially just standardizing our sample variance based upon the null or assumed population variance. In each of these cases, the criteria to accept the alternate, for a two-tailed test, we take our alpha and we split it evenly between the left tail and the right tail. So we put alpha over 2 into each of the tails. This value here is equal to chi squared alpha over 2 with n minus 1 degrees of freedom. And this value over here is chi squared 1 minus alpha over 2 with n minus 1 degrees of freedom. So if we're in the tails, meaning our test statistic is greater than chi squared alpha over 2 with n minus 1 degrees of freedom, or our test statistic is less than chi squared 1 minus alpha over 2 with n minus 1 degrees of freedom. If either of those is true, then we'll accept the alternate hypothesis. For an upper-tailed test, we put all of our alpha, our uncertainty, into the upper tail. And if we exceed chi squared alpha with n minus 1 degrees of freedom, then we can accept the alternate hypothesis and we can claim that the true population variance is greater than what we proposed or hypothesized in the null hypothesis. And then for a lower-tailed test, if we get our test statistic is below some critical value, chi squared 1 minus alpha with n minus 1 degrees of freedom, then we will accept the alternate hypothesis and claim that the population variance is less than our proposed or null hypothesis population variance. So let's go through this example. Is there evidence to support that the variance is greater than 0.25 square mils? We're going to use an alpha of 0.10. Our hypothesis, the null hypothesis, is the population variance is 0.25, and the alternate hypothesis, the variance is greater than 0.25. If we take our sample and we compute statistics, we get there's 10 samples. Our sample standard deviation is 0.588. We can use our sample statistics to compute a test statistic, and when we do this, we get that our test statistic is 12.45. That means that if we took our sample standard deviation and we standardized it into a chi-squared variable, it would be 12.45, assuming that the population variance is 0.25. Now we're performing an upper-tailed test, so we choose this middle option. We have to show, in order to support or accept the alternate hypothesis, that our chi-squared variable is to the right of this critical value, the critical value being chi-squared alpha with n minus 1 degrees of freedom. Again, our test statistic is 12.45, so that's right about there. We can compute the critical point. That is if we put 10% of the population into the tail, alpha equals 0.1. That value, that critical value that we have to exceed in order to accept the alternate hypothesis, is 14.68. We can get that, by the way, by using tables in the back of your book in Appendix A, or you can use the chi-squared.inv.rt for right tail function in Excel. If you were doing a left tail, a lower tailed test, then you could just use the chi-squared.inv function without the RT. But we have 9 degrees of freedom, and when you do that in Excel, you get 14.68. The conclusion, because our test statistic of 12.45 is not down in the tail, is not in the critical region, it does not exceed, for this upper tail test, 14.68, we reject the alternate and fail to reject the null hypothesis. Now let's compute a p-value for this test, because a more common way to perform these hypothesis tests is to calculate a p-value. The p-value is just the probability that the distribution is above your test statistic. So again, our test statistic is there. It's about 12.45. The p-value is just the percentage or proportion of the distribution above your test statistic. And so that area is the p-value. We can do this in Excel using the chi-squared.dist.rightTail function, and we put in 12.45 with 9 degrees of freedom, and we get that the p-value is 0.189. You can also perform these hypothesis tests using confidence intervals. I'm not going to show an example of this in this screencast, but it's certainly possible, and this is how people used to do it before computing tools were readily available. So here we have the alternate hypothesis is a two-tailed test, a not equal to sign, so we would create a two-tailed confidence interval. If the null variance, sigma naught squared, is not within our confidence interval, then we can accept the alternate hypothesis. However, if sigma naught squared is within our confidence interval, that means that it's not unlikely to get that population variance based upon your sample variance, and so you would reject the alternate and fail to reject the null hypothesis. So hopefully you learned a little bit more about how you can perform hypothesis tests on the variance in this screencast.